Hi there, welcome to Raelene Maths. In this video I'm going to show you how to use a sign chart to help you to sketch a polynomial function. Here's a polynomial function and it's the product of a cubic times a linear times a quadratic function. In a previous video we solved that polynomial less than or equal to 0 as an inequality. In fact, here's where I did it. This is the working out and I used the x-axis to record the three roots of the polynomial, the three zeros, and then we created three factors along the side plus the four regions created by three cuts on the x-axis, which gave us 4 times 3, which is 12 cells. We recorded a positive or a negative in each cell to indicate whether that factor in that region, set of x values, was positive or negative. We've come up with a row indicating negative, positive, positive, negative for the sign of the p of x, y coordinate. So let's import that sign chart or table of results and see how to build the graph from here. We now know that in region 1, when x is less than -1, the y coordinates on the p of x graph will be negative. So the graph of p of x will lie below the x-axis and it will not lie above. So I'm going to shade out above the x-axis so that I don't try to draw the polynomial graph here. In region 2, between the x values of -1 and 1, the y values on the p of x graph are positive, so the graph lies above and not below the x-axis. So I'm going to block out region 2 lying below the x-axis. In region 3, for x between 1 and 2, the y values are again positive, so the graph again lies above the x-axis, and therefore I will block out or shade below the x-axis. Lastly, in region 4, I will shade above the x-axis because the y values given by the sign chart for p of x are negative. Now I'm ready to introduce my y-axis, so I'm going to tidy up the sign chart a little bit. If you can't do this because you're not using a tablet, you may want to draw a new x-axis with the shading. So I'm ready to introduce my y-axis, and the y-axis is x equal to 0. And so I'm going to put it in the appropriate region and make it a little bit bigger than the other vertical lines so it stands out. And once I have the y-axis, I'm interested in coming up with the y-intercept. By definition, the y-intercept is the intersection of the y-axis with the graph. The equation of the y-axis is x equal to 0, and that's why we substitute x with 0 to get the y-intercept. So the y-intercept is going to be given by p of 0, which is going to be 0 plus 1, which is 1 all cubed, times 2 minus 0, times -1 all squared, which is equal to positive 2. Now it's interesting to note the sign of y when x is 0 because that's consistent information from our sign chart. When x is equal to 0, the y values are all positive, or in that region the y values are positive, and so we're going to get a y-intercept that corresponds or confirms our sign chart. The next thing we want to know is the end behavior. And so to come up with the end behavior, we really want to see what the leading term of the polynomial is. To do this, we're not going to fully expand the polynomial. We are merely going to look at the leading term from each of the factors. If we were to expand the red binomial cubed, we would get x cubed. And then the leading term of the blue factor is -x. And the leading term of the expanded green factor is x squared. This is not the same expression as the original p of x because this is just the very first term of the expanded form. So I'm just going to put plus ... to indicate that there are lower degree terms, powers of x involved here. So if we were to expand this, we would see that the leading term is going to be -x to the 6, and the x to the 6 graph looks like this. -x to the 6 is a vertical reflection, and we are going to have end behavior that has the same ends as the -x to the 6th graph. So we're going to have something over here like this and like this, indicating as x approaches -infinity, going to the left, the height, y, or p of x, also goes to -infinity, left and down that is. Meanwhile, as x approaches positive infinity, y approaches -infinity. So that's just a pseudo-calculus or limit notation to indicate the end behavior of this polynomial. The next thing we need to consider is the multiplicity of the root, or the number of times each x-intercept occurs, and that occurs according to the exponent on the factor. So the cubic function is going to look like a cubic with a horizontal tangent, and depending on the direction of approach coming up to that x-intercept, we will either have the first version or the second version. The key is that at x equal to -1, we will have a horizontal tangent. And we see that from the sign chart and the end behavior, the graph has to come like this and continue like this. If the blocks were reversed, if the shading was reversed, we would have the other version of the x plus 1 cubic function or factor. We also have a linear factor for 2 minus x, which means that there is no horizontal tangent when x is 2. That just suggests that the graph is going smoothly through without flattening. And so the graph is going to do something like this and continue down without having any horizontal tangent behavior. The quadratic factor suggests that we have a horizontal tangent again because the graph is going to bounce around, and depending on the direction that we approach x equal to 1, we will either have a concave parabola-like shape, concave up or concave down. And because of the sign chart, we see that the graph is going to be like this. We have to fit together the rest of the graph, and we don't exactly know where this point is going to be. I'm just going to put a question mark here. This is the realm of calculus, and so we are only estimating, guessing where that might be. Similarly, we have to fit the rest of this graph together, and we might assume that the turning point or the maximum point is at this y-intercept, which happens to already be sketched. That's one approach, but it could also be that the graph does something like this and reaches higher before coming down, or it could go through the y-intercept, turn around afterwards, and come down like this. Any of those three versions are possibilities, and until we do some calculus to find where we have a maximum point in this region, we don't know which one is the actual graph. What we will do, though, is look at the graph using graphing technology to see what indeed it is. So we have the graph x plus 1 all cubed times 2 minus x times x minus 1 all squared, and we do in fact see the end behavior of negative x to the 6, the horizontal tangent at x equal to -1. We have the y-intercept at y equal to 2, and the turning point is just ever so slightly after that. So to assume that the y-intercept is the turning point or the maximum point is not accurate in this example. But we do have a turning point at x equal to 1 because we had that parabola-like horizontal tangent behavior. We turn around higher than my graph indicated, and we come smoothly through like the linear behavior. So we can see that the sign chart as a tool came up with a fairly accurate model. Just going to eliminate these portions of the graphs that were not accurate, and we were able to come up with, as pre-calculusly as possible, a graph of the polynomial using the end behavior, the sign chart as tools, and the intercepts, both the x and the y-intercepts. If you like the video, click like and subscribe to my channel. Stay tuned for more sign charts, graphing of polynomials, and rational functions in upcoming videos in the series. Thanks for checking out Raelene Maths.